All right, so when we look at naming to finish up our chapter here on nomenclature, one of the things that's important that we check is, of course, functional groups. So here you'll see that we have a chart that has specific functional groups. Now, that brings us to the question of what is a functional group? Well, a functional group is something that, or a group of atoms that reacts in a specific way that's independent of the molecule. So what that means really is that you can have this huge molecule with lots of carbons and lots of hydrogens and all this kind of stuff. But if you can pick out the functional group, then you'll know something about how that molecule is going to react. So it's important then that we recognize which functional groups that we have here. And so what you should be concerned with is that you need to look through the chart and make sure that you can recognize certain functional groups. So for instance, you can see things like a carboxylic acid, which is second on the right from the top. All right, so those things are important. So these different types of functional groups, they include alkanes and alkenes, right? These are types of molecules and alkynes that react in specific ways, and so we will discuss later on how these are going to react and some of the different transformations that we can make using these specific functional groups. So make sure that you view the chart and that you learn which is which on this. So you should be familiar with things like an alcohol, a carboxylic acid, maybe something that looks like an ester, right? All these different groups. You should look an ether, for instance, where the cursor is. These are things that you should make sure that you know what they are. So make sure that you look at functional groups. Now, that brings us to our last point here in naming, and this is naming alkyl halides. So one of the things that's important with this is that we want to notice where the bromine is, and then the carbon that is directly adjacent to it. Notice that is 1 over from the bromine, so if we use the letter alpha, or the symbol for alpha here to denote that that is the alpha carbon, meaning that that carbon is 1 away from our bromine. Now, one of the things that you should also notice on here is that the bromine is attached to the alpha carbon that is also a secondary carbon. In other words, it has only 2 other carbons that are bound to it. So in turn, this makes this what we refer to as a secondary alkyl halide. All right, so you should get used to calling things in this sort of fashion, whereas the bromine is attached to a carbon that is secondary, and therefore it is a secondary alkyl halide, right? And we can go further. The ones that are out away from it in 2 more away, these are what we call beta hydrogens and beta carbons, right? These are 2 away from the bromine, or 1 away from your alpha carbon. And then we can go even further out, right? And we can go to our gamma carbon, which is 3 away. So first, make sure that you recognize what the halogen is attached to so that you can begin to classify halogens in a more broader sense, as far as this would be a secondary alkyl halide. If it was tertiary, it would be attached to, it would be what we call a tertiary alkyl halide. So when naming alkyl halides, what you want to do is, for instance, use the sort of bromo, chloro, iodo, all of those, fluoro, those guys there for when you stick on the substituent. So you, of course, need to identify the locant, right? And the other thing that's important is that remember that alkyl halides, alkyl groups, and ethers, if you remember what that is from the last slide, have the same priority. And so what you want to do is number such that you get the lowest overall number, right? So for this one here, notice that that is 3 from the left for the chlorine, but if we go from the right side, we have 2 there. So that gives us basically the directionality that we need to go. We need to list the methyl as the 2 position there, right? So that becomes the 4-chloro. So in this case, we're going to name it just like we did before. We are going to name this using the parent, which is 6 carbons. So we have hexane, so that would be a hexane there. And then we just need to identify where all of our pieces are, right? So we have our chloro that is in position number 4. So list your groups, when you name this, that's the other thing that's important, is when you name it, you want to list it alphabetically. So that means the chlorine goes first, right? So 4-chloro, and then we just need to list our methyl groups. We have 2 of them, so they are dimethyl. Remember, the D in this dimethyl does not count in the nomenclature for alphabet, right? So this becomes 4-chloro 2,3-dimethyl hexane. Now, sometimes you do need to use the alphabet when making a decision. And so this is basically what happens when you have the same distance on either side before your substituent. So when you have 2 things that are equidistant, you must determine the direction that you go based off of um, the alphabet here. So what you can see here is that we have a methyl and a bromo, and so since the B for the bromine comes first here before M, we need to number from the right hand side, right? So this tells us which way we need to go. Now remember, you're only going to do this when you have 2 substituents from the same distance. So here in this case, we see that bromine needs to get the lower number in this way. So you would number from the right. Now, the last little bit that we need to discuss when naming is priorities. So remember the list that we had of different functional groups. Well, it turns out that different functional groups have different priorities in how we name them. So you can see that in this case, the double bond is the one that has the higher priority, right? Remember that we said that the alkyl groups, alkyl halides, and ethers all have the same kind of priority, right? So this double bond is one step above that, and so it has the higher priority. So what that means is that we have to number such that we give the double bond the actual lowest number. So again, what you want to do here, this dictates that you must start from the left-hand side such that you get a number 2 for the starting point of your double bond, and not a number 3 if you were to have started from the right-hand side. So even though the bromine is there, remember that you need to follow the priorities here, and you're going to number according to which one should get the more priority. So the highest priority here should always get the lowest number. So one thing that you can do, and I'm going to show you, is how we can figure out which ones have the highest priority. Again, you need to remember what your functional groups are, because this is important when we name, right? You must remember which groups are which, because you can't determine the priority of them unless you are able to recognize different groups. So again, make sure that you recognize which groups should have different priorities and number in accordance to that, making sure that the highest priority group gets the lowest number. Also, don't forget about things like E and Z when you're naming double bonds, right? We can't let those go, so we need to include that. So notice also that we put the locant there for the double bond, and we're all done. Now, this is how you use or determine priorities here. There is a chart that you see to your right hand side. It's also in your book, and it is in the slides that you have downloaded or able to download on D2L. So we look at our priorities here, and we can see if we go down to the bottom, actually, kind of ignore where my cursor is, we have the double bonds down there. You can see that we have XR and OR. Those are your ethers, alkyl halides, and alkyl groups. Right, and you can see one above that is the double bond. So that there is the reason why we chose to give the double bond the higher priority. So you want to make sure that you kind of use this chart to help you in naming. Right now, mostly you just need to be concerned with alkyl halides, alkyl groups, double and triple bonds. and that's pretty much all you need to worry about for that at the moment. All right, so going to our next chapter, which is going to talk about acids and bases, we're going to kind of review a lot of stuff that's from Gen Chem here, and we're going to actually need to first give sort of an acid-base definition, what qualifies as an acid or a base, and we need to kind of work through a few things here. We also have alternate descriptions such as Lewis acids and Lewis bases we need to talk about. We need to talk about things that affect acidity, so what can make something more acidic or less acidic. And then we have equilibrium reactions that we need to discuss as well. Which direction should the equilibrium be pushed? And we need to talk about the basically amines and how they react and what they do, and then how resonance can actually influence acidity. So there's quite a bit to discuss in this chapter, so hang on tight. All right, so first thing is just getting an understanding of acid-base reactions and some basic definitions here. You want to think of an acid-base reaction of basically a base attacking an acid, and so we're going to use an arrow. So we have here an arrow that looks like this, full arrow going from the negative charge to the positive charge. And then so you can draw the resulting product, right? And so remember, in this case, we're going to look at the Bronsted-Lowry base definition, which is a substance that can accept a proton, right? And then we have the acid, which is a substance that can donate a proton. So if we take a more real example, and we notice we have sodium hydroxide over here, and notice that the arrows from the negative charge are going to attack the hydrogen that is coming off of our acid. This is the carboxylic acid. And notice now that the electrons in between the bond to the oxygen and hydrogen are going to go over to the oxygen. So you need to draw two arrows for this. You have one arrow that comes from the negative charge to the hydrogen, and then one that comes from the hydrogen to the oxygen. And then you can go in a reverse direction where you can have the conjugate base now attack the water itself and push the equilibrium back to the left, right? So you can see that water in this case is now acting as your acid. And you can see again we have the same sort of description here for all of our arrows, right? So notice that the electrons here in between the oxygen hydrogen go back to the oxygen to give us the OH minus. Now, this brings us to the Lewis acid, Lewis base theory. This is probably one of the most important aspects or concepts in organic that you need to understand. And that is because you can pretty much figure your way through any type of mechanism knowing the difference between a Lewis acid and a Lewis base. So here you can see the water has lone pairs. It is acting as a Lewis base because it's a substance that can donate a pair of electrons to something that is acting as a Lewis acid, right? Like the boron, which has a vacant p orbital, and it has all these electron withdrawing groups on there, right? So the fluorines, very electronegative, pulling density away from it. And so this is now something that can accept a pair of electrons. And then once this happens, we just draw the arrow just like we did the last time, except we're not breaking another bond, so we'd only have one arrow to show going to the right. And we get a Lewis acid base pair. Now looking down at the bottom example, notice again we have a carbon that is electron deficient, right? The electron density is being pulled by the more electronegative bromine, and so then the negatively charged sulfur can attack that partial positive of carbon there. So things like H plus is also a Lewis acid and a Bronsted acid, right? So you just depends on on what definition you're using. You can also note that as an example here, we have acetone, and we have these lone pairs that are on acetone. And so if I treat this with HCl, notice that HCl here is going to actually protonate the oxygen on there. So the lone pair on the oxygen is going to act as our Lewis base and is going to attack the hydrogen from HCl, and we end up with a final product like this, right? So this is now a Lewis acid base reaction that we see here. Also done with a Bronsted acid, right? So depends on, again, your sort of definition. So things like Magnesium 2 plus is a Lewis acid. Other things, for instance, like titanium tetrachloride, TiCl4, very strong Lewis acid. Bf3, as you saw above, very strong Lewis acid. So anything that is electron deficient is often able to act as a Lewis acid, right? So tin chloride is another one. There are several examples that you can find in your text as well. In general, oxygen and nitrogen, because they have lone pairs, are going to act as a Lewis base. They're going to use those lone pairs like you see above with the acetone attacking the acid there, right? So those lone pairs are often used as a Lewis base to attack a Lewis acid or acid of some sort, right? So make sure you go and review different Lewis acids and Lewis bases in the in-reading portion. All right, this brings us to our last topic, and this is what we consider acid strength. How do we define it? What do we use? Well, we use a Ka value, right? So Ka tells you the strength of the acid, so a high Ka value means that you have a strong acid, right? So where do we get Ka? Well, if we look at a acid-base equilibrium reaction type situation, you would see that we put the products, the concentration of the products, over the concentration of the reactants. And so this is what we would use to get our Ka value. So if we considered just the sort of tried and true generic sort of equation here for acid in water, right? We have an equilibrium, and we have the, of course, H3O plus that happens, and then plus we have the A minus, right? And so if we wanted to note that we're in water, so we have a lot of water on both sides, and so since it's on both sides, we're just going to kind of ignore it here, so it can kind of cancel out. So we're looking at HA into the water there, which gives us our H3O plus, and so if we were to write Ka on this, we're not going to include water. And what we see is we have H3O plus, A minus, and then we have HA concentration at the bottom. And so what you can see is that if you have a large Ka value, that means that your HA concentration is very small, right? So that means you have a strong acid. And so typically what that means is that strong acids are going to shift the equilibrium to the right, which equals a larger Ka value. Weaker acids are going to have an increased HA concentration, right? So our equilibrium therefore is shifted to the left, and this would then give you a smaller Ka value because you're dividing by a larger number, of course, right? So what are sort of typical Ka values that you would see? And so that's one of the things that's kind of important to discuss, in the fact that a lot of Ka values that you would see, for instance, strong acids, they have Ka values that are very high. So like sulfuric acid, HCl, right, those guys, all the different strong acids, they have Ka values that are like 10 to the 2, between 10 to the 7, right? So 1 times 10 to the 2, 1 times 10 to the, or 9, sorry, excuse me. And so those are very large numbers, and so it often becomes kind of a pain to write out those numbers all the time, right? So instead what we're going to do is use what's called a pKa value, which is just the negative log of that Ka value, right? So this comes in the point where if you have now a smaller pKa value, then you have a stronger acid. So you kind of need to get familiar with using pKa values, because that's what we're going to use mostly within this course, are different pKa values for different groups. So make sure that you get comfortable using pKa values instead of Ka values. So what we do, though, is we sort of go back to our functional groups, and we give sort of generic pKa values to a group of functional groups, right? So for instance, alcohols. Alcohols typically have pKa values that are around 16, right? Remember, the lower the Ka value, the stronger the acid. So as an example, strong acids have pKa values that are negative, right? So HCl has a pKa value of -7, right? So that just kind of gives you an idea of what we're looking at here. Another important one that you should know, and we will go over a list of them that are important for you to know pKa value-wise, are carboxylic acids, for instance. They have pKa values that are typically around 9. So like acetic acid is 4.76, right? So very close to 5. I don't know if I said 9, but 5 actually there. So those are also important. So instead of remembering specific pKa values, what is important is to remember pKa values of functional groups, right? So it's a lot easier to understand or remember pKa values of functional groups than it is very specific pKa values. Now, sometimes you'll get used to it and you'll remember them, but remember to use functional groups for pKa values. Don't try to remember all of them. Thanks for listening.